let me draw your attention to a few administrative matters. So everyone should have received your graded homework set back. And please take a minute to review that, compare your answers with the key, and as soon as possible, let the TAs or myself know if you have any questions or if there were any perceived errors with the grading. Obviously, the point of the homework is to dig deeper into the course material and then provide a dress rehearsal of sorts in preparation for the midterm. So please try to take some time to iron out any points that you're unclear about between now and the midterm next week. The midterm, as you can see from the schedule, will be next week, Thursday. The TAs will organize 2 office hours between now and then at times that work with as many people as possible. The format of the midterm will be, it will start at the same time as class, 8:30. It will be designed to be 90 minutes, but you will have a full 2 hours. So it would be 8:30 to 10:30. And we'll triple check that there's no event booked immediately after class. That seems to never be the case. The first question of the midterm, I will tell you right now, will be, and this is a tradition dating back even to my time as a student, you will be given a blank periodic table and you will fill in the D block. That will be question 1. So that's the hint. Learn that. And if you, because that, so that goes hand in hand with another point, which is that it will be a closed note, closed book exam. If you forget something for the periodic table, then we don't want to double penalize you on later electron counting problems or anything like that. So you can ask a TA to essentially grade it on the spot or fill in the blanks, but for a point penalty. So that's how that will work. You'll be given a periodic table, learn it. You might think this is very tedious, but I can tell you from firsthand experience, because I was a student and now I teach the material, it's very useful to know the relationship between metals when you're in a lecture, when you're looking at problems of the day. So commit that to memory. And I assure you it will benefit you in your future career in science. Another few administrative points before we jump into the material. So the syllabus is slightly updated. We did a little bit of accounting, reaccounting or accounting adjustment. So we will call the day 8 lecture Carbines Part 2. And then today's lecture will be called Principles of Catalysis and Ancillary Ligand Design. We've updated or will update the names of the associated worksheets to reflect what was actually covered and the readings that are associated with those topics. On Tuesday, Camille will lecture on hydrogenation, and that will be the last material that you're responsible for on the midterm, and then we'll pick things up the following week with carbonylation. Everything is shifted back 1 week, and that will mean that the CH activation lecture that I would normally give, I may not give, but it would depend. Sometimes guest speakers have conflicts that come up at the last minute. So we'll just keep that pending for the minute and we can fill it in as needed. If you're really chomping at the bit to hear that lecture, we have the recording of last year's that we can, if we don't get to it, then we'll just add that to the Canvas as not a required activity to do, but something if you're interested, you can listen to. Any questions on course administration, midterm? Everything clear? All right.
I was going to get access to slides.
Oh, thanks for that, Philip. Yeah, there was a question about having access to the notes, and I will make all of the notes up until, well, I guess all of the notes for my parts available this afternoon, so you'll have time over the weekend and next week to review them. They'll just be exported as a PDF, so you'll have record of that. Great, thanks, Will. Any other questions?
Midterm covered the guest section.
Yes, I think in general, the midterm and the final will cover guest lecture material, particularly to the extent that the guest lectures like reinforce things that we cover elsewhere in the class. Thanks for that question. Okay, let's jump right in with principles of catalysis and ancillary ligand design. We'll start out with some content that I think will be review for most people, but it is still helpful to have rigorous definitions and common ground that we're all working from moving forward. I think you probably learned this in Gen Chem in undergrad or maybe even high school, the definition of a catalyst. And in the context of this class, we're going to be talking about inorganic or organometallic catalysts. A catalyst is any substance that will increase the rate of a chemical reaction by lowering the activation barrier associated with that reaction without itself being consumed. We normally think about that in terms of something that can do its job over and over again and turn over multiple times, but that isn't part of the intrinsic definition as Oswald defined in the late 1800s. During the reactions that we'll consider in class throughout the rest of the semester or the quarter, the catalyst will undergo a series of elementary steps, elementary organometallic processes that in the end will regenerate the catalyst. And an important thing to consider is it will need to regenerate the catalyst not only in terms of atomic or molecular connectivity, but also in terms of the oxidation state of the metal involved. So in the overall oxidative process where the metal might decrease its oxidation state from 0 to 2, then you would need to reoxidize it to turn it over with a terminal oxidant. And again, some review here. What will the overall potential energy surface look like for a catalytic reaction or a step that is catalyzed? It's important to disentangle thermodynamics and kinetics here. And I'm often surprised as I go forward in my career how difficult it is sometimes, or how these two concepts sometimes get confused or talked about interchangeably when in fact they're distinct. So if we consider a generic A plus B goes to C plus D reaction, then based on the connectivity of the starting materials and the products, then that reaction will have some thermodynamic parameters associated with it, delta H, delta S, delta G. And for a given transformation, you can tabulate that just based on the bonds that are broken and the bonds that are formed. And then associated with that reaction, depending on the mechanism that's at play, then we have the kinetics. And here we're considering delta H double dagger, delta S double dagger, and delta G double dagger. And so, changing the mechanism by which A plus B goes to C plus D reaction can, of course, change the activation barrier associated with that process, and that is a kinetic acceleration. Sorry, I'm having a little problem with my computer. Okay. And in some of the catalytic reactions that we'll consider, it's important to distinguish that addition of a metal catalyst or perturbation of the ligand structure can accelerate the rate of a reaction. And that can be a result of several potential changes. And two that are important to have clear in your mind are transition state stabilization. That's essentially equivalent to the statement that the reaction will become faster as this energy goes down. Or actually, I should highlight the blue because that's the catalytic one. Versus ground state destabilization of the intermediate that's involved. And both of those can lead to an empirical result of a reaction running faster. And this is discussed in some depth in the Hartwig textbook. So I would direct you to that portion of the textbook if you want to read more about that. Okay, so with those terms clearly defined. So let me add one more comment before we go further. So I think one of the challenges you encounter in your research career is, let's say you want to do a catalytic reaction that does not work, and your task is to get it to work. Then it cannot work for reasons that are thermodynamic in nature or kinetic in nature, right? And it's important to have that clear in your mind. So a reaction not working for kinetic reasons basically means that there's a barrier that you're failing to climb to get to slide down to the product, which intrinsically thermodynamically downhill. A reaction can also not work because it is just thermodynamically uphill, and you have no thermodynamic driving force. So even in a hypothetical world where it were to happen based on the principle of microscopic reversibility, the reverse would happen, and you'd be stuck with. Sorry. So an example would be a closed, just as one example you could consider, like a hydroamination, classical hydroamination of an olefin. This is a reaction that intrinsically is thermodynamically nearly thermoneutral, and depending on factors like the concentration of the reaction components and the temperature, you can, I'll leave that to you to think through how changing concentrations of starting materials or temperature might favor one side of the equilibrium versus the other. But this is a reaction that, based on the connectivity of the starting material products, is in principle close to thermoneutral. So if you want to have thermodynamic driving force in this process, then you could imagine how would you favor the right side of the equation here? Wenji, what do you think?
Add in many equivalents of the
Perfect. Yeah. So you have based on Le Chatelier's principle, if you increase the concentration of, let's say, the amine component, then you will drive the reaction towards the right. And so those are thermodynamic changes, concentration of one of the components. If you're thinking about changing the ligand structure on the metal, that you're only affecting the kinetics of the process, right? Okay. Let's consider now a general catalytic cycle. This I've taken directly out of the Hartwig textbook, and I like it because it's general enough that we can make some overarching observations, but specific enough in a few key points that often go overlooked that we can have a meaningful discussion. So we're going to enter the catalytic cycle here, and we'll just walk through this and then discuss a few manifestations of this. We're going to enter the catalytic cycle here. And if you read the literature, you'll note that, let's say for a cross-coupling reaction, you'll see that typical recipe, bless you, will be something like palladium DBA plus a phosphine ligand, palladium acetate plus a phosphine ligand. In that case, you'll typically see some excess of the phosphine ligand. the palladium DBA or palladium acetate in those cases is not the true active catalyst, but it's what we would call a pre-catalyst because it needs to undergo some series of steps to get on cycle. And sometimes that, I think, when you're entering the field for the first time is maybe not intrinsically obvious or can be confusing because you could see, for example, a common point of confusion is that, let's say you're doing a cross coupling, the oxidation state of the pre-catalyst is palladium +2, the catalytic cycle itself, the active form is palladium 0, and you might look at the pre-catalyst and think, maybe it's a palladium 2,4 cycle because what palladium 2 is what's going on. No, there's some series of steps that need to happen before you get to your active on-site species. So that's what is nicely defined here in the Hartwig schematic. Now, once you've got your active catalyst, there are a number of things that can go wrong or can be inhibitory. So one is in a case where you're generating the catalyst in situ from mixing the metal and the ligand, then often you will have some molar excess of the ligand, and that can lead to formation of inactive species that are multiply ligated by the ligand. So that's expressed here, and those lie off cycle. There's no way without dissociating that ligand that you can push arrows to complete the catalytic cycle. So there's now a ligand dissociation step that needs to happen. And we've seen how that can manifest in a number of different elementary processes throughout the class, needing to free up a coordination site to allow an elementary step to take place. Okay, now a generic substrate, which is just labeled S here. This is not sulfur, but just substrate, will engage with the metal catalyst. And now here too, there's something that can go wrong or can be complicating, which is that you can have multiple equivalents of the substrate bind, and then that can lead you to an inactive form. So think, for example, the reaction that you're trying to do is some kind of alkene functionalization. That's of course near and dear to our hearts. Then typically a form of the metal catalyst where 2 or even 3 of the alkenes are coordinated is not the active form. That's sitting off cycle. And then you'll need to lose some equivalence of alkene to get back on cycle. And that can lead to more complicated rate dependencies on concentration of starting materials when you have these off cycle reservoirs. So some generic elementary step, which we just call elementary step 1, will then take place. And now we'll get to an intermediate that is just denoted as lnm.I in this cycle. So this can complete the catalytic cycle by undergoing a second generic elementary step 2, to make a product bound form of the metal catalyst, which can dissociate product to close the catalytic cycle. Alternatively, things can go wrong at this stage too. For example, if we consider this example, if we consider the case I just mentioned, where you're doing some alkene functionalization, then maybe your intermediate is an alkyl metal species that can undergo a beta hydride elimination that is undesired, and that can lead you to an inactive form of the catalyst. So in practice, catalysis is on paper often denoted in a very elegant way, and in practice is a network of a lot of on-cycle and off-cycle processes that need to be controlled in order for productive things to happen in the flask. Okay, let's consider now, going back to our day 8 worksheet, problem of the day number 1, which touches on this idea of pre-catalysts and how you activate them to get on cycle. Okay, so let's consider the dichloroiron 2 pincer complex shown here. And the information you're given is that this pre-catalyst, after an appropriate activation step, can promote the anti-Markovnikov hydroboration of alkenes. And this is notable in the research world because this is a process that we often associate with precious metals, but now here we're doing it with an earth abundant base metal. So let's brainstorm methods how you could get from the inactive iron 2 form to the active iron 0 form in situ. Well, it doesn't have to be in situ, I guess, but how do we reduce this down? What are some reagents or strategies we can use? And then part B asks you to propose a plausible catalytic, but of course here I mean catalytic cycle for the reaction. So take a minute to think about that and discuss with your neighbor, and then we'll go from there. Connection issues. What's going on? Okay, Elin, let's get us started here with some thoughts. What do you think?
You can either use some base and add some example they use like breathing.
Grignard, okay. Let's walk through this Grignard example. What do you think is going to happen with Grignard? What kind of Grignard do you want to use? Okay, give me a Grignard. Methyl, ethyl, propyl, phenyl. Terbutyl, okay.
So we'll just add two and then like one proton to that. So it will
Is this what you want?
Somehow reduce.
Okay, and then you want reductive elimination. Transmetallation, reductive elimination, and is everybody happy with this?
Can we just add something reducing in there like zinc or plain magnesium?
Okay. Zinc metal, or you said magnesium metal. Where then now the byproduct, if we are trying to be rigorous, the corresponding zinc chloride. Madison, you cringed with this Grignard choice. What makes you uncomfortable about this?
I mean, like, just in terms of out of economy, and I don't know, it seems like you get some side products having alkyl groups on there, but I'm not sure. I don't know, it might be possible.
Might be plausible.
Don't they have trans to do reductive elimination? Or
They should be cissoid for reductive elimination. Yeah. If it were me, I'd probably opt for maybe a simpler Grignard. Let's say ethyl. Because then the reductive elimination is going to be a little bit less painful with methyl. That CSP3 reductive elimination makes me a little bit uneasy, even from iron, where you're able to engage radical pathways.
longer and like kind of make the beat then once like this is where you get the worry.
That is a very interesting suggestion. So from the way the question is worded, I think the implication here is that the HB pin itself is not sufficiently reducing that we can get on, that we can directly reduce in the way that Philip was suggesting. But what if we make the corresponding 8 complex now we're going to associate OR here. Now we're building up negative charge. So this is more reducing for the same principles that we talked about before. Have some cation associated with it. And then the question will be, is this sufficiently reducing that we can get, what do you think the product of this would be? In this case, Madison. Let's say you're as reducing now as a lithium hydride or lithium aluminum hydride, or I'm not saying you are, but let's say you were, then what would you expect as an intermediate? Okay, beautiful. And now you can lose H2 to get on cycle minus H2. And then there's maybe one approach that's sort of a combination between the first and second option, where you transmetallate on, let's say, one alkyl group, and then you get a beta hydride elimination, and then you can push arrows to get on cycle that way. Then you just need some base to capture the metal hydride. Good. Any other thoughts on that? Questions? And this is, in fact, a very astute suggestion by Madison, because this is the strategy that they use for this paper. Let me pull up the reference so I can write it down. And the whole paper is actually about this activation strategy of making 8 complex through use of t-butoxide to make more reducing boron hydride and silyl hydride species. So this is Beautiful. Okay, and the catalytic cycle here, help me push some arrows. Dylan.
We have the alkene coordinate.
Okay, so we've got iron 0, and the first step you want to coordinate the alkene.
I think so.
Okay. Then what? Doesn't feel right. Okay. What's the only other option? What else do you have in solution?
The HB pin.
Aha. Okay. And if you coordinate that, what would potentially happen?
Have a hydride and then the boron.
Beautiful. So you're saying this is going to undergo oxidative addition, if I understood you correctly. Now you have a boral hydride species. We're up at the iron +2 oxidation state now. And now, when you coordinate your alkene, now you have some options here. I'm going to draw this as going. Okay, so get us home here, Dylan.
So we could have the hydride add in to the alkene, and then those electrons would add on to boron.
Okay, so migratory insertion of the hydride. And then what's the, if you didn't know, what would be the other option that could migrate in? Dylan.
We have boron migrate in.
Okay, and why do you prefer hydride?
Less happy being just the hydride, I would figure.
Okay. In principle, both here are possible, and you see both in the hydrocorrelation and hydrosilation literature. But hydride is fine to draw here. And then what to close the cycle?
Just reductive elimination.
Beautiful. Now you just reductively eliminate. And out pops your product. Now you can, as we just alluded to, you can draw some of these steps in different orders, but it should ultimately collapse to being the same steps. And that's a common mode of reactivity for many hydrofunctionalization systems: low valent metal, oxidative addition, and then some migratory insertion followed by some reductive elimination. We'll see that again in the context of hydrogenation. We'll see that again in the context of some of the hydroformylation. Questions on that? Yes.
I wonder, why is the iron 0 species the active catalyst? Because I feel
As
like
opposed to,
you can still write another mechanism where you start with just like a displacement from iron 2, and then just do the I'm just thinking maybe from the intermediate shown there,
I'm not sure
I
how.
think it would be reasonable potentially to and one of the points, that I didn't go into just in the interest of time is that the oxidation state assignment of iron here is not that clear cut because these and pincer ligands are redox non-innocent, so they can themselves absorb some electrons. So whether we call this an iron 0,2 redox couple or a 1,3 redox couple probably isn't critical. But I think if you're thinking in the opposite direction, that it would be a higher oxidation state iron redox couple, a 3,5 or something, then that is probably less likely because the iron is just not going to be nucleophilic enough to get the job done.
Did they observe that regiochemistry in this Nature paper? Where it's like a Markovnikov?
Yes, that's right. This specific Nature Chem paper is on that activation strategy. The chemistry itself is from the lab of Paul Chirek, and then Jen Wong has some related work. So we'll upload those references if you're interested in seeing the scope. Yeah, great questions. Okay, a few more quick hitting definitions. You'll hear in talks in the literature, turnover number, turnover frequency. Turnover number is a metric that describes catalyst stability. It's the moles of product divided by moles of catalyst. So like in our lab, sometimes we're doing nickel catalysis and we're barely turning over 5 times. We use, 10 mole% catalyst and get 50% yield of the desired product. On commercial applications of homogeneous catalysis, you can get tens of thousands or hundreds of thousands of turnovers. Turnover frequency is a metric that describes the kinetic performance of the reaction. That is turnover number as a function of time. So that's the first is telling you how stable the catalyst is. Second is telling you how quickly it can do its job. So let's continue this theme of defining terms that we'll encounter later in the class in the literature. So on the kinetic side, one point that I think the Hartwig textbook takes special care to try to clarify, and that I, since we're using that as our textbook, I'll take a minute just to comment on, is descriptors of the kinetic behavior and kinetic properties of a catalytic reaction. So a catalytic reaction that reaches steady state, remember that in steady state, if you have a multi-step catalytic cycle like the one shown above, then in practice, every step of the cycle is taking place with the same rate, bless you. And so when we're talking about which of those steps is the slow step, it's not really meaningful to say which is the rate determining step, because all of them have the same rate. That's why in the more mechanistic part of the organometallic catalysis community, they prefer this term of turnover limiting step. Turnover limiting step is the step that has the smallest pseudo first order rate constant associated with it. So if we're assuming we're in a pseudo first order regime, then it's basically asking the question of which of those steps intrinsically has the highest barrier, assuming that we have excess of the various reagents that we need. So I think that's intuitive. What's the hardest step to do? That's the step that is holding up this overall cycle, where in practice, each step at steady state has the same rate. And then the catalyst resting state is going to refer to a catalytic species that's present in the highest concentration. And so if you think about the overall potential energy surface, this is the species that is at the lowest energy, most stable before the turnover limiting step. It's not necessarily the species immediately preceding the turnover limiting step, because you can have a situation where you go, or from your perspective, you're going uphill to a higher energy intermediate to the transition state, and this would be the resting state down here. And in principle, the catalyst resting state, if it's a well-defined single species, it's not partitioned among multiple resting states, then it can be readily observable. That doesn't always work out in practice for various reasons we can discuss if you're curious about that. But you know, when luck's on your side, you could just take an NMR and directly observe the catalyst resting state as a clear defined species. Sometimes in our lab we've had that kind of luck, sometimes we haven't. And then as a consequence of these points we just discussed, you can think this through for yourself, but the overall rate of the catalytic cycle cannot exceed the rate defined by the rate constant of the turnover limiting step times the maximum of the concentration of the reagents, times the concentration of the reagents at the beginning of the reaction. That makes sense. Okay, let's talk now about homogeneous versus heterogeneous catalysis. Most of this class focuses on homogeneous catalysis. Of course, heterogeneous catalysis is equally important. It's mechanistically oftentimes more complex. Mechanisms are harder to elucidate, and principles that we care about as organic chemists, like selectivity, are often more difficult to control. Each has its advantages and disadvantages. Let's talk quickly about those, and then how to distinguish between them for a reaction that a priori you don't know which mode, which regime you're in. Okay, so homogeneous. Let's talk first about homogeneous catalysis. So these are some of the reactions that we're familiar with: cross couplings, homogeneous hydrogenations. The advantages here are selectivity, tunability, and rigorous understanding of the mechanism. So if you put yourself in the shoes of a process chemist and you're scaling up a Suzuki reaction, then homogeneous catalysis has the advantage of when things break, when you have a plant with $3 million of starting materials in it and the cycle is not proceeding, that you know the order of steps, you know the actors and potential bad actors at play, and you can make changes on the fly in order to get the reaction to take place. And we have this beautiful ability since the seminal discovery by Wilkinson in the 1960s of using triphenylphosphine to solubilize metal catalysts. We have this ability through the ligands to tune the steric and electronic profile of the metal center. Ligands are hands as chemists at the transition state for bond making and bond breaking. So that's the advantage. So the advantages of homogeneous catalysis. The drawbacks, and process chemists will be the first to tell you this, are separation. So by definition, these metal catalysts are operating in the same phase as your reactants and products. And thus, downstream of that, it can be very difficult to purge the metal impurities from these product streams. And often this requires actually separate discrete steps for sequestering the metal through various resins and additives. Okay, now if we look at the other side, heterogeneous catalysis, this has the advantage of offering extreme levels of reactivity, both turnover frequency and turnover number, low cost, recyclability. So heterogeneous catalysis, I think these are this includes society supporting technology like the Haber-Bosch process, as just one example, that operate at such extreme levels of efficiency and have such low profit margins that it's very difficult to envision achieving that in a homogeneous sense. So the disadvantages here, and why many folks in this department are less drawn to heterogeneous catalysis, is that it's often non-selective. When it is non-selective, it's harder to know how to tune it to improve selectivity because you don't have this advantage of well-defined ligands. There's been a movement in the literature to hybrid catalytic strategies where you could imagine a nanoparticle-based catalyst that has a ligand that is familiar from homogeneous catalysis, but this is still emerging technology. Okay, let's jump now into problem of the day number 2 to discuss how we differentiate between homogeneous and heterogeneous catalysis. Problem of the day 2 from the day 8 worksheet. I will put that up if you don't have that worksheet with you. Just a moment. So this asks us to consider a unusual looking hydrogenation reaction from the lab of our textbook author, John Hartwig, where we're taking a diaryl ether in the presence of a nickel 2 pre-catalyst, fairly extreme by the standards of organic chemists conditions, 120 degrees, long reaction time. And in the presence of H2, you see that we're able to hydrogenate this OC bond that we normally wouldn't think of. This is not a benzyl ether, remember, this is diaryl ether. We wouldn't normally associate this with being a site of hydrogenation, but here we're able to observe hydrogenation. So there are some signaling elements here that might make you suspicious. If you're a referee or a journal editor, you might think, I'm not sure a priori whether this would be homogeneous or whether maybe we're precipitating some nickel nanoparticles and the heterogeneous, and it's actually a heterogeneous process. So some of the signaling elements would be like fairly high temperature, fairly long reaction time. When we look and we ask what ligands are on nickel, we say, oh, there's nothing that strongly sigma donating. It's this dialkyl nickel precursor. The alkyl groups are going to get reductively eliminated, CMEDA, which we've covered before in class, but I'll draw the structure. That's not a super strongly coordinating ligand. We might not expect that to ligate efficiently at nickel under these conditions. So we don't know a priori. So then the question asks you to design some experiments that would allow you to disambiguate between a homogeneous and a heterogeneous process. So let's take a minute to think about that, discuss with your neighbor, and then we'll brainstorm collectively brainstorm as a class. Maybe as you're talking amongst yourself, one point I'll emphasize here is the mechanism, for the purpose of this discussion, the mechanism of this reaction is not important. It's just this question of how will we distinguish between homogeneous and heterogeneous. Okay, let's get some ideas down on paper. Philip, what do you think? Give me one experiment that if this were you would run.
You can filter your reaction solution.
Okay. That's a good one. Filtration. So in practice, I assume you're thinking you'll start the reaction, ramp up to that temperature, and then filter at that stage, take the filtrate and see if that filtrate can promote the reaction. Is that the
If
idea?
it's nanoparticles, you wouldn't be able to tell because you won't see them filtered. Something else you could do is like take like solid phase nickel, and then see if you can have influences by surface area of your like heterogeneous catalyst.
Okay, test metallic nickel. That's
Right.
the
And
crux
then
of the
see
idea.
if you can get like enhancement of your catalytic species by increased surface area, for example.
Okay. Annabelle, what do you think?
Add more nickel catalyst.
Add more nickel catalyst, then what would you expect to happen?
Acceleration to
If it's home, right, okay, so this is an interesting point. I think if you have a fairly well kinetically behaved reaction, I think your idea, if I understand you correctly, is you'd say, if it's a heterogeneous process, the rate is going to be a function of the surface area of the nanoparticles or the metal particles. And that surface area will increase, will not increase linearly as you increase concentration of the progenitor catalyst, whereas it's a homogeneous process, you would. Is that the crux of it? Okay. I think that's kinetics can definitely help here. And I think one, quick indicator that you might be in a nanoparticulate regime is if you just measure substrate conversion over time and you see sigmoidal kinetics with a long induction period. That can be a signaling element. Alex?
I had a couple ideas. One,
Okay.
depending on if it's nano versus microparticles, stir rate might have an effect on the actual kinetics of the process.
Okay.
So if you don't stir the reaction versus stir it really fast, you see a difference in kinetics. It's likely an indicator of heterogeneity.
Let me just add this to.
Yeah, and then I don't remember the name of the technique, but is there not a way to look at the diffraction of light to see if it's colloidal versus just a homogeneous solution?
Okay, yeah, or I think in general, using some type of spectroscopic or microscopic technique. So for example, if you analyze the reaction mixture with any number of microscopies, with TEM, you will get evidence, you would see evidence for nanoparticles. You wouldn't necessarily know then if they're the main driver of reactivity, but you know they're there and you know to investigate further. Any other thoughts? Any volunteers?
Mercury drop.
Okay, mercury, tell us how that works, Shenghua, mercury drop test.
So if there's like metallic particle, mercury will dissolve. You would not expect reactivity from a
Heterogeneous catalyst will form aggregates or amalgams with mercury and become deactivated, whereas homogeneous won't. It's not as easy as it used to be these days to get your hands on mercury. We have some in the lab from the chemical museum that we inherited from Julius Riebeck. We've done this, Camille's done this experiment recently, I think. And then the opposite of a mercury drop test is you can take, this is not the only way to do this experiment, but this is just one example. You can take dibenzocyclooctatetraene, and this will strongly inhibit homogeneous processes, but not heterogeneous processes. Any other ideas? These are all great suggestions. One more that I'll throw out there is, it's called a three-phase test. This was developed by our colleague Julius Riebeck early in his career. The idea here is that if you immobilize your substrate and you're in a heterogeneous regime, now your catalyst is in one phase, your you have your solution phase and your starting material is in a separate phase. Now, we know that reactions can take place at liquid-solid interface, but solid-solid interface is very, very slow kinetics. Essentially, that will completely suppress the reaction rate. So if you change the phase from 2-phase to 3-phase and reactivity drops off, then that can be a sign that you're in a heterogeneous regime. Super. Any questions on that or other ideas that we didn't get to? Okay, we'll go through this part quickly. Again, more definitions as it relates to asymmetric catalysis. So a key concept in asymmetric catalysis is taking prochiral substituents and then converting them to molecules that contain typically point chirality, but also you can imagine axial or planar chirality as well. What we refer to here as prochiral in the context of point chirality. So it's a position on an achiral molecule that becomes a chiral center upon adding addition of an achiral group to one face or replacing one group by a new group. That's a little bit of a mouthful. But the key idea there is that, let's say you're doing an alkene hydrogenation, then you have the alkene as the prochiral component. If you're doing a CH activation, as we can see on this right case, then you can have alkyl substituents that are prochiral. An important point of terminology is this Re versus psi phase. Sometimes I've heard people say that Re always goes to R and psi always goes to S. That's not right. Sometimes that's the case, sometimes it's not. Re versus psi is essentially a consequence of doing priority assignments on a planar molecule. So we follow our same priority assignment rules. And then if our priority assignment goes counterclockwise, then that is the so if we put our planar molecule in the plane, make a priority assignment, then the priority assignment goes in the counterclockwise way, then that is the psi phase, just an analogy to S, and the opposite is true of the Re phase. In terms of product outcomes from enantioselective catalytic reactions, I think the two descriptors we're most familiar with are EE and ER. In the early days of enantioselective or asymmetric synthesis in general, we're very drawn to using this measurement EE. And the reason is because, unlike today, the way that they would make a measurement of the level of enantiomer enrichment of a chiral material was using optical rotation. And if you look at this formula for optical purity, you'll see that EE ends up directly falling out of an optical rotation measurement. So it's a convenient measurement to use when your primary analytical technique is optical rotation. Nowadays, nobody uses optical rotation unless an editor or a reviewer asks you to do it at the end of your project. You're using SFC or LC or GC with chiral columns. So some members of the community have strongly pushed that we instead report an enantiomeric ratio. And why is that advantageous to EE? It's because an enantiomeric ratio has a direct correlation to the actual delta delta G double dagger values, as opposed to EE, which has only an indirect version. So when you take an EE measurement and you want to say something about the energy barriers, you actually need to first convert it to ER. And so people are now moving towards reporting ER directly. In the context of kinetic resolutions, there's a measurement that I won't say too much about, but it's called a selectivity factor, or S. And this just has to do with the fact that for a kinetic resolution where you have a racemic mixture of a chiral molecule, and you're reacting only one of those enantiomers away, then EE is not necessarily a useful measurement, because if you run that reaction to very low conversion, then your EE of your starting mixture is low, but it doesn't really mean the reaction is not selective. So it takes into the effect that for kinetic resolution, if you run it to higher and higher conversion, you intrinsically can enrich the EE of the starting material. Some useful rules of thumb here in terms of stereoselectivity are the delta G double dagger values at room temperature for a reaction that has 90% EE. We're talking about transition state differentiation, major minor, of only 2 kcals per mole. 80%, 1.4 kcals per mole. So in this community of asymmetric catalysis, people often obsess about 90% EE. And if you actually break that down into the energies involved, then there's only a fleeting difference between, let's say, 88% EE and 90% EE. Okay, let's talk about now some types of catalytic asymmetric reactions, different regimes that one can be in. There are, I think, two cases we'll consider in class. One is where you have a single enantiodetermining step. This is by far the simplest. And the examples here are things like atom and group transfer reactions. So for example, oxidation of sulfides, some epoxidations like Jacobson type epoxidation. The kinetics here are very simple because the reactive form of the chiral metal catalyst is essentially just reacting via a bimolecular collision with the substrate. There aren't discrete intermediates involved that we need to account for in terms of different diastereomers and their respective stabilities. And so this is the simplest case, and the kinetics reflect that this is the simplest situation, where you basically have 2 diastereomeric transition states with different energies associated with them. And then the major product that's observed, the major enantiomer that's observed, is the one that has the lower barrier associated with it. But life is often not so simple, and probably the regime that we're in more often in research is this second regime, where it's an overarching descriptor, and then there are several sub scenarios here that we'll walk through. So this regime is where we have reversibility prior to the enantiodetermining step. And earlier I didn't define this, but enantiodetermining step is defined as the first irreversible step that takes place through a diastereomeric transition state. So it's not intrinsically the step where, let's say, your new chiral center, your new CC bond, for instance, is formed, where that bond is formed. That step could be reversible, and a downstream step, like even dissociation of the product, could be your enantiodetermining step. Okay, so let's consider now reactions with reversibility prior to the enantiodetermining step. They're much more complicated, although we can still think through it in logical terms. So let's consider scenario 1, where the case study is hydrogenation of olefins, and Camille will talk more about hydrogenation of olefins with a chiral catalyst. Now you have a situation where prior to the enantiodetermining step, or maybe I should be more precise here. So now you have a couple different situations. You can have a situation where the binding of the alkene to the catalyst is enantiodetermining, or where C hydrogen bond formation is enantiodetermining. So scenario 1 here is that we're starting in this purple box, and we have 2 options. We can bind either of the 2 faces of the alkene. And then once we bind, we're committed. It's not going backwards. You see that the downstream steps have a lower barrier than this initial binding event. So once we bind, we're committed, and thus the coordination, the formation of the metal olefin complexes is the enantiomer determining step. That is probably the most simple sub-scenario within this regime too. Now, the other scenario is where you have interconversion of these two diastereomeric intermediates being significantly faster than the reactions that form products. And we call this overall regime Curtin-Hammett control. Sometimes you'll hear people refer to Curtin-Hammett specifically as a situation where the less stable intermediate reacts through the lower barrier transition state to give the major product. I think that's the most clear-cut demonstration of the Curtin-Hammett principle, but it is, strictly speaking, Curtin-Hammett describes this whole collection of possibilities here. So now you're interconverting between these intermediates faster, and then downstream steps, and the downstream steps, those barriers and the relative stabilities of the intermediates are dictating which product is formed. And within this regime, there are even two subtypes that I think you can probably get a sense for. One is that the more stable intermediate reacts faster. That's what I've represented here. But you could also imagine the opposite, the more stable reacts slower. And so that's what I said when people often refer to this sub-scenario B as the clearest demonstration of Curtin-Hammett control. Okay, any questions on that before we move on? I realize these are speaking in generalities here, so it's as we work through some examples, it will become clearer and clearer. So let's talk about now descriptors for ligands and how these ancillary ligands manifest and perturb steric and electronic properties of the metal. So we've talked briefly about phosphines, and we've actually introduced some of these terms or concepts, and now we'll define them rigorously. So phosphines and NHC ligands, I think, are, and as well as some nitrogen-based ligands. These are the most popular, most privileged ligands that we use for reaction development and discovery. Phosphines, in particular, they benefit from having relatively strong coordination to the metal through a soft-soft match. They're strong sigma donors, as Josh defined it. It's because the energies of the lone pair associated with phosphine are relatively high. And these, of course, can dramatically affect properties of the metal center. So let's consider now the case of bisphosphines. We've seen this before in the class in a few examples. So bisphosphines can be described using a parameter called natural bite angle. Natural bite angle is calculated by just thinking about the metal itself using molecular mechanics calculations, and then finding the minimum, the energy minimized structure and determining the angle between the phosphorus atoms. Now, the natural bite angle is not the same as the bite angle when the ligand is coordinated to the metal. That's an important distinction. What happens in practice is that when a bidentate ligand coordinates to a metal, the angle that the bite angle that it forms is dominated by the metal's preferred binding geometry. So square planar, you'll see bite angles tend towards 90 degrees. So that's why the natural bite angle is more of a readout of what the ligand likes to do in the absence of the metal. And actually the delta between natural bite angle and observed bite angle is an interesting thing to think about, because that is essentially telling you how much strain the ligand is accumulating as it's coordinating to the metal. Okay, so let's see some examples now of natural bite angle. let's just try to see how our intuition compares to reality. Let's try to rank order this set of three, DPPE, Xanthos, and BINAP in terms of increasing bite angle. What do you think there, Hannah? Okay, BINAP is the biggest.
Boss and then DPP.
Okay. Then Xanthos and then DPP. Does anybody agree or disagree with Hannah?
I disagree.
Hannah disagrees with Hannah. Okay.
I think
Hannah number two. What do you like to issue a rebuttal?
I think Xanthos is biggest.
Okay. I've tried to draw that here to give a sense for that. So Xanthos is the biggest, and then what?
Then BINAP, then DP.
Beautiful. Xanthos is in fact the bite angle is so wide, it's what we call a trans-spanning ligand, meaning that for a square planar metal, it is able to coordinate at two positions trans to one another. It's I think close to the limiting case of trans-spanning in the sense that it can also be cis-spanning. So I think somewhere around here, 105 to 115, that's sort of the limit for bite angle for something to be trans-spanning. And on the surface, I think it's interesting you're first drawn to BINAP. BINAP is an interesting one because you could imagine, depending on how it prefers to sit, it could have a very wide bite angle or it could have a kind of narrow bite angle, right? And so the bite angle here is correlated to another concept in ligand design, which is the dihedral angle, essentially the angle between the two planes, the two naphthol planes. So as we talked about, bisphosphines can sit either cis-spanning or trans-spanning. And in general, let's say within the cis-spanning series, then wide bite angles will promote reductive elimination through the principle of squeezing out. Phosphines are interesting because they have a relatively slow barrier to inversion as compared to nitrogen, for example. So in the 1970s, this was accurately quantitated for the first time by Mislow from Mislow-Evans name reaction fame. And after it was recognized that the barrier to inversion is quite slow, then people picked up on the fact that that gives you the opportunity to develop ligands that are chiral at phosphorus. And if you think about the timing, I mentioned this earlier, that Wilkinson's first use of triphenylphosphine in homogeneous catalysis was in the 60s. Now, about at the same time, people are realizing that phosphines can be chiral at phosphorus, and this would provide the opportunity for phosphines to be purveyors of stereochemical information in an antioselective catalysis. And indeed, that was taken up by Knowles, ultimately leading to the Nobel Prize for him. The first manifestation here was this monodentate chiral at P complex that offered moderate enantioselectivity and hydrogenation. And then this was developed into the bidentate C2 symmetric ligand that folks still use today called dipamp. And this dipamp ligand was the was the ligand that was used for the first commercial enantioselective hydrogenation en route to L-DOPA that won Knowles the Nobel Prize for enantioselective catalysis. So that's some discussion of coordination properties and asymmetric catalysis. Let's also think about the bonding and electronics. Here, I'll ask you to sort of take a step back, just things we've covered earlier in the structure and bonding lecture. So some of this is just review for you. You can consult those lecture notes as well. So in terms of how phosphines interact with metal catalysts, remember they have a sigma donating interaction, but also they're capable of serving as pi acceptors. In the early days, it was thought that the 3D, unoccupied 3D orbital would be primarily responsible for the pi accepting character. But I think as time passed, there was a growing appreciation that actually the sigma star antibonding orbitals in the case of like triphenylphosphine, the aryl P sigma star antibonding orbital is predominantly responsible for the pi accepting character. And then the most accurate description from an MO depiction is a sigma star antibonding orbital 3D mixing model, which I've tried to represent here. So if for a first approximation, you can just think about sigma star antibonding orbital as being the primary pi accepting component, recognizing that this 3D mixing model is in practice more accurate. Okay, let's see how this manifests in problem of the day number 3 from the day 8 worksheet. So here we're considering a series of nickel carbonyl complexes with different phosphine ligands. Part A is fairly straightforward. We can just probably do that together, and then I'll give you a second to think about part B and discuss that with your neighbors. So part A just asks, let's compare phosphine ligated nickel tris carbonyl to simple nickel tetracarbonyl, which Josh talked about in his lecture, and ask CO stretching frequency, what's going to happen? So let's get that one down, and then you have a minute to think about part B here. So Cindy, what do you think?
Lower.
Why?
Just sigma donating group. Manifest more so it has stronger bonding with CO and less CO.
Beautiful. So in general, phosphines are sigma donors, strong sigma donors. They make the electron center more electron rich, more capable of pi back bonding. That leads to a lower CO stretching. Okay, now let's consider this series of ligands. Tri-substituted phosphine series, T-butyl, phenyl, and anoxy. Let's try to rank order these. Chenghua, what do we think here?
It's from lowest to highest terbutyl, phenol, and the phosphate, I think.
From lowest to highest, T-butyl, lowest, and then you said triphenyl, and then the phosphite. Okay, so first, can you walk us through your logic in the T-butyl versus phenyl comparison?
Terbutyl phosphine is more donating than triphenol.
Okay, why?
Because have like acyl
substituents on phosphorus is more donating to the phosphorus than sp2 centers in general.
Okay. Everybody buy that? And then walk us through, let's compare phosphite, the triphenyl phosphite versus triphenyl phosphine. What are you thinking there?
Oxygen substituent is very electron withdrawing from the phosphorus. So I think it should reduce the sigma donating character of the phosphorus.
Okay, oxygen, you're thinking oxygen's a more electronegative atom and will have, is that your line of thinking?
Yeah, that's.
So what if somebody came back to you and said, well, what about the lone pairs? They have those lone pairs there. They could potentially donate some electrons through pi donation to the phosphine.
That's true too, but I think phosphites usually have like very high chemical shifts on phosphorus and R relative to the phosphines. So these are two competing factors. I just guessed that they should be more withdrawing, but I might be wrong.
Okay, yeah, phosphites are. So we've got, sorry about that. Okay, so A we said is lower, and then we're arranging this series, and as Shenghua said, here are some numbers here, and let me put one more for comparison. A very extreme case is trifluorophosphine. And here, trifluorophosphine is almost the same as nickel carbonyl itself. That's telling you trifluorophosphine is basically like a CO ligand in disguise. And these are all in units of inverse weight number. So this is an interesting point. Phosphorus heteroatom bonds, phosphite or PF, these have significantly lower energy sigma star antibonding orbitals. And as a result, they're much stronger pi acceptors than the corresponding phosphine series. So yeah, one way to think about that is that bonding interaction is relatively weak, meaning the antibonding interaction is low energy and thus it wants to soak up electrons from the metal center. Super. Any questions on that? So understanding these trends, how sigma donating and alkyl phosphine or an aryl phosphine versus aryl phosphite, these are very important, I think, and this is something that we'll come back to again and again. Okay, a few quick hitters here. Steric descriptors. We've introduced briefly this concept of cone angle, and cone angle is just defined, or cone angle falls out of the fact that if you think about what a phosphine ligand coordinated to a metal looks like in 3 dimensions, it resembles indeed a cone. And in the early days, Chadwick Tolman actually built wooden models and measured with a protractor manually these cone angles. So the original cone angle values that sometimes are still quoted were actually measured with a protractor. This is very useful as a first pass descriptor of the steric influence of the ligand, but it has some drawbacks. One is conformational in nature. You imagine that phosphines, in fact, are dynamic. There's a lot of rotatable bonds, and if things are rotated out of the way versus in the way, they can have very different cone angles. And cone angle is an inadequate descriptor when you talk about unsymmetrically substituted phosphine ligands, because measuring the cone angle in one direction ends up being different than measuring it in the opposite direction. So in the early days, people recognized this problem. They came up with a quite awkward descriptor that nobody uses today, but I have it here just for posterity's sake, and this is called solid angle. Solid angle is the same concept as doing a hand puppet show. You know, we've all, as a kid, you put a light behind your hand, and then you see what the shadow of your hand looks like on a sheet, and then you can make your hand a dog. I hope everybody did this. If you don't, then if you didn't when you were a kid, then then just pretend I'm not, just close your, plug your ears now. So anyway, so solid angle is the same as a principle as a hand puppet. You treat the metal as the source of light. The ligand is your hand in this analogy. And then you're just measuring what percentage of the area is in a shaded region versus a non-shaded region. And then you can back calculate solid angle. So the drawbacks are that this is very non-intuitive. That's probably already obvious. And it's not easy to measure. So this has largely been supplanted by something we'll cover in a moment called buried volume, percent buried volume. There are other classical organic descriptors that of steric bulk that you might want to superimpose onto phosphine ligands. And indeed, sometimes this is valuable. So from classical physical organic chemistry, not even talking here about organometallics, you've learned things like inference values, A values, chart and Taft parameters. And so you can superimpose that into understanding ligand steric bulk. And that can be helpful in some contexts, but some of the same issues arise. And one issue is that these types of descriptors also do not accurately capture substituents that are unsymmetrical in nature. And so one set of descriptors that has come into vogue in the organometallic community that I'll introduce very briefly, and then I think we'll hear more about it from one of the Wikipedia projects later in the semester, is stereomole parameters. So stereomole parameters were originally introduced not in the context of coordination chemistry at all, but just as means of quantitating steric bulk of groups of substituents that are unsymmetric in nature. And so stereomole parameters, it describes a set of descriptors that can capture the multidimensionality of some substituents. So we consider here an isopropyl group. 3 stereomole descriptors that come out of this are shown here: the B1, the B5, and L. B1 is essentially, so if my pen is the bond to the isopropyl group, then B1 is the orthogonal to it, the distance to the shortest point. B5 is the distance to the longest point that the isopropyl group exhibits. And then L is essentially the measurement here of how far that projects out into space. So the only point, it's not important to remember these definitions, but just remember that for a given substituent, you can define a constellation of descriptors, and then those descriptors you can feed into more sophisticated models. And the reference here that I'll draw your attention to from earlier in the notes is this Kraken database from the work of Tobias Gensch, Matt Sigman, and Alan Asperu-Gusick, who've done comprehensive, based on DFT computation, comprehensive ligand parameterization of 1,558 ligands, monophosphine ligands, stereomole parameters, cone angles, electron density parameters, et cetera, et cetera. And so one of the key points that phosphines exhibit is their ability to dissociate and reassociate, which can be very important in catalysis, as we've already seen. And the ability to dissociate is correlated both to their steric and electronic properties. We've seen before that bulky phosphines, by virtue of their sterics, tend to want to coordinate trans to one another. And then another class of powerful ligands are N-heterocyclic carbines, or NHCs. In comparison to phosphines, they're stronger sigma donors and weaker pi acceptors. You can think of this, if you want to continue like Josh's line of reasoning, they're stronger sigma donors by virtue of the fact that the electrons that engage in bonding interaction are higher in energy as compared to phosphines. So NHCs are more nucleophilic than phosphines. And then being here in San Diego, I would be remiss if I didn't highlight a related class of stable carbines, which are called CACs. cyclic alkyl aminocarbines developed by the lab of our neighbor Guy Bertrand at UCSD. And we've used these in the lab. We have several of these in the lab. And the key thing to remember here is that you essentially have a point mutation from a nitrogen to a carbon, NHC to CAC. And what does that do? How does that manifest in terms of properties? CACs are more extremely amphiphilic. They're more donating and more accepting. We saw this in Josh's lecture in the case of the DF ligand. It's more donating and more accepting. So CACs have this more extreme behavior, which can be very useful in tuning the metals property. Why are they stronger pi acceptors? I think an intuitive way for me to think about it is that remember you have these lone pairs in the case of NHCs that donate electron density to stabilize the unfilled p orbital of the carbene. And now one of those is missing in the CAC, and thus that orbital is destabilized. So the pi accepting orbital goes to a lower energy. That makes sense. And one of the principles to remember is that in general, there are exceptions to this that we'll talk about, but in general, NHCs or CACs, those metal carbene bonds are sufficiently strong that they typically do not dissociate under the reaction conditions. And because NHCs do not look at all like cones, they look more like birds. Cone angle is like a totally meaningless descriptor for NHCs. And so Steve Nolan, several years back now, came up with a descriptor called percent buried volume, which has really caught a lot of traction in the community, where percent buried volume is just defined as the amount of volume filled if you imagine the metal as a center of a sphere and define the sphere as being 3.5 angstroms, a radius of 3.5 angstroms. It can be calculated conveniently online using this tool here. And the nice thing is that it works with symmetrical, it works with unsymmetrical, it works with phosphines, it works with NHCs. There are some things that it does not totally capture, and so there's still opportunities for innovation here. It doesn't capture the electrostatic potential of the sphere, it just captures the steric impression of the sphere. It doesn't capture conformational dynamics, although recent work by Matt Sigman, Abby Doyle, and others has shown that you can look at all possible conformers and then consider Boltzmann weighted distributions of the conformers, and that is useful. And then it's also dependent on how you define R. Josh showed an example of something that's similar here to this steric or topology map. You can do this for steric bulk, you can do this for electron density. These are also quite useful here. Okay, let me, okay, we're a couple minutes over. So let me, we're at the end of these notes, but I left a couple things to think about here. So one is, I'll put up this problem of the day for day 10. And I would just, you also have it from your handout. I'll ask you to think about it for homework. Will probably be, and you can discuss it with your lab mates, and then we can have a very quick discussion of it in the next class, which is putting yourself in the shoes of somebody working in pharma or ag or something like that, where you're asked to develop this Higishi couplet under nickel catalysis, and asked to develop to identify what ligands and precatalysts you put in a screen that would be maximally informative in terms of information that you gathered. So there's lots of different ways to think about it. No right, no wrong answer. So think about it yourself, and then we'll discuss that quickly at the beginning of the next class. All right, have a great weekend, everybody. I'll stay after if there are any additional questions.